This is part 3 of the live proving in Lean of my PrimeSieve. And I'm just going to go ahead and jump in. Let's see. I'm going to make this a little smaller. Nope, not how you do it. Hopefully that's still readable. Okay, so since last time, I've actually got quite a bit of work done. I'll just go ahead and bring up the main thing. So the kind of the core idea now, it was here before, but sorry, start over. Kind of the core idea is that you have this notion of a prime generator, and it at every step it has a function. So the type is an a prime generator. A class alpha or a type alpha is a prime generator if given an instance of it, you can produce a p that is a nat prime. So a natural number that is prime. So it produces a prime at every step. It has an initial state, and it has a next state that, turns the crank basically. And I added this hypothesis now, or this was in the PrimeSieve, and now it's moved to the prime generator, that for every step, there isn't a prime that exists that is greater than the prime at step p, and then less than the prime at the next step. So in other words, it's a continuous, or it generates consecutive primes starting from wherever it started. That's the basic idea. I have a very simple implementation now that proves all this it's called SimpleGen, and it just uses Lean's built-in feature, or I guess MATLab's built-in feature called NatFind, which will just, as it says here, if you have a decidable predicate, then it will just look for the next number. So it kind of just like does some kind of internal for loop and figures out the next prime given the current prime. So that's very basic. That is not a PrimeSieve, but it is a prime generator, and it's this statement right here that the SimpleGen is an instance of PrimeGen supplies all the proofs of that. So we supply whatever the state is. So here's the structure. It has a P and a C. So the P is a prime, and then C is the minimal prime greater than. That's the type of the value of P. So the type is actually min prime greater than, and that type is just takes a natural number and it produces a natural number, and that natural number is prime, and it is in fact a prime greater than n. So this is a proof that this relation holds between n and p, that a prime is p is a prime greater than n. And then same thing, that it's the minimum such thing, and this is another version of the minimum. Both of these are supplied by, these two facts are supplied by NatFind. So all we have to do is say, P is NatFind of this, first prove that it exists, which there's some little proof up here that given a number, there is a next prime, and that follows from the infinite prime, the proof that there are infinite primes. Yeah. Anyway, that's basically how it works. And so then once we have that existence proof, we can use it to find things. We can use that same spec to prove that P is prime, because that's what we're looking for as a prime. We can, and then NatFind itself proves that it is the minimal, and in two different ways of stating that. And then from there, I wound up proving the thing. So that this right here supplies the proof that P and next P are consecutive primes. If you haven't seen this yet, I'm not gonna explain this yet, because we'll be doing this a lot in just a minute. So I'm just gonna skip right through this. But basically, the proof is that no prime between. I like to put it in English first before I write this, because it's easy to get lost doing these little tactics. So no prime q exists between gp and g next p y, and that would imply that prime greater than p. But hmin says that next, the next one, nat find finds the minimal example. So blah blah blah. So how do you prove it? Well, what you do is you look over here, and you can see that in order to prove this statement, we have to prove this, so that not exists, blah blah blah. And then as you step through it, you see that changes over there. So we unfold the we start with this definition of next. So we unfold the definition of next. Okay, then you get a big mess. We simplify that. That simplifies all the way down to this. For all x that are prime, g.p is less than x, and not x is less than the next thing, right? So it's, I guess, between these values. It's weird you have to write it this way, but it's saying it's x is greater than p, and x is less than the next p, the c, the candidate prime. So we have to say a for all. So we got to fill in that for all. We introduce a q, and then you want to say for all what? So introducing a q replaces this x with a q, and then if you want to suck up this part, this implicate, or the left part of the implication, you can assume that there's a q that is greater than g.p, and so that's what this does. So intro q and q greater than g.p, greater than p. And so now we have those two assertions, and then it says, so this is all that was left to prove. This is what was left. This right here is what there was before we introduced those two things. So if we go back here, that's this part now. So basically, we got rid of these two things and moved them up into hypotheses, right? By introducing them, we said if the goal is to prove for all x of something, then say we'll pick an arbitrary x, and then if we can prove it for an arbitrary instance with no other assumptions, then other than this, then it must be true for all of them, right? So that's how you prove that. So you just introduce one, and then the way we prove this is by contradiction. So we're going to make a new hypothesis. This is not true, and then we have to prove false. So there we go. So we have q is less than this, blah blah blah. And then the way I decided to prove that is exactly this. So we now have a q. This is our hypothesis that a q is less than the next prime. So now we have to prove that, and also that it is, so it's greater than p. So we have both of the conditions here, right? So we've assumed this exists. Now we're going to improve. We're going to have a contradiction, and the contradiction is from h-min. So let's bring that into scope. We have h0 is that thing. It's the proof itself is attached to the structure, right? This right here is just there's no data at runtime, but at compile time, it's a proof. So it's a proof that this thing is true. And so then we just bring that into scope. We simplify that, which is basically just, it goes from prime GT to like nat prime and whatever. And then we apply this hypothesis at HQ. So because it says for all q less than, the thing we just brought into scope was for all q less than greater than p and nat prime, right? Well, we have a nat prime called q and this blah blah blah. So we just apply that, and now we've simplified it. So so now HQ got simplified to nat prime q. So if we can show it's nat prime, well, okay, we have that. But I guess I didn't have to actually insert this. Like, we just have it, right? So we'll see. Oh no, we're using it here. So so because it's an n prime. N prime is this site up here that says nat prime. It's just a subtype of prime. Yeah, it's a subtype of nat where the numbers are prime. And so you get these wrapper types, and you have to say, like, see this little arrow pointing up? is saying that the value inside that subtype, right, the nat that's corresponding to that n prime is prime, right, which is kind of obvious, right? That is the actual definition of q.prop, right? So q is n prime, and n prime includes that property, right? So by applying this, right, we can derive this fact, so that right, if we go here, we just proved this, just stated it, and then this is the proof right here. It's a rule that's built in, and then I wanted to flip this thing around so it would match this statement. I want to put a not sign in front of this statement, and I have this statement right here, and so I have this is a prime, so on, blah 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 blah. Anyway, from all this context, then Aesop can solve it. Oh, weird. All right. Yeah. So now I have this and this, and these are contradictory statements. So I say contradiction, and that just like looks around to find the two things that are contradictory. Okay. So that was that. Anyway, like I wasn't going to go through too much of that, but I'll not do that anymore. Anyway, so then that proves that SimpleGen follows this rule that it generates the next consecutive prime, all these things together, and then we can actually try it out. So this is just a little helper I made that lets you apply a function multiple times over and over again to an initial input. So this says apply this function 10 times to this input and generates these numbers, right? Including 0. I probably should do n-1. Yeah, this should probably be n-1. But whatever. 0. Yeah. Yeah, it's actually producing 11, so this should be n-1. So then that should produce 10 primes. It does, and there they are. Those are the first 10 primes, and this does the range 10. Okay, so anyway, the point is that the prime SimpleGen works, but until it would have worked even if I hadn't proven this. Except that this takes a prime gen, right? So in order to even call primes, you have to have a prime gen. That's the idea. All right, so I'm gonna check that in, that little change I just made. So check that in, and just minor fixes to fixes in PrimeGen, and I'll upload that. This is at TangentStorm, github.com, TangentStorm TreeSieve. I will TreeSieve. I'll put up. There's a lot. This doesn't really talk about the prime part of it, but PrimeGen, PrimeSieve, and then this is the actual implementation. All right, so let's look at PrimeSieve real quick. I did this before, and but I'm just going to review what the current state is. I am making a video about this for Summer of Math Exposition, so I want to have some record for anybody who wants the details. I'll probably do another code review later and then actually edit it when it's all done, but good practice for that. All right, so we've changed PrimeGen, so now we have to restart this file. Lean is integrated with VS Code, and it live resets. It takes a little time on my computer. I don't know if this is a universal experience, but a little slow. But then after a few seconds, it works out, and then it's live. Right? It's all cached. All right, so I'm going to go through this one a little faster, I think. But as of today, a PrimeSieve. It says the PrimeSieve is a PrimeGen. That used to be something that you supplied here. But what's going to happen instead is that at the bottom of this file, I'm going to write a theorem that says that if it is a PrimeSieve, then you can automatically implement prime gen, and it follows from these three things, right? So that at every step we generate prime. This is the new prime. It's greater than the old prime, and there's no prime in between, which are the three things we just saw. So from this, it should be fairly easy to write, to write that a PrimeSieve is a prime gen, and then we can call primes on it and actually get primes out of it. But what is a PrimeSieve? Well, it's in two parts. First of all, the actual state is here. So this is the thing that you move from step to step, and rather than just generating a prime, it has a prime associated with it, but the next thing is not necessarily a prime. So C is the candidate, right? It's a natural number. And if you supply these three facts about it, if you can make these three proofs, then PrimeSieve itself can prove from one of these theorems down here that C is prime, right? It can also find all these things. Actually, this I think is. Oh, no, it's not. So like this is fairly easy once you know what the actual implementation is, right? So you have to say, well, I have some state in this. I'm going to model a PrimeSieve however I want internally in terms of like data, data structures and algorithms and whatnot. As long as it does these three things, I don't have to worry about proving that it's actually working. I just have to prove these little smaller things, that I'm somehow modeling this set of numbers that are all the primes less than. I'm sorry, it's the set of numbers that are co-prime. That is, they have no prime factors less than or equal to this number p. Right, so that's that. And if C is a member of that set, and it is the minimum of that set, so C and R, and it's the minimum, then C is prime. And if it's greater than P, then we can actually prove that there was no prime in the middle. So if it's the minimum of this set, then the PrimeSieve itself proves that it's the next consecutive prime. And so that's what these three proofs in here. So we have a C prime lemma, which is like this. I'm not going to go through it. We have a no prime factors implies no factors. That's just a helper. I probably should call this theorem, right? It's like no skip prime, right? And that's it. And then the fact that it's greater is actually supplied by the implementation. So this one should probably be a theorem. Theorem and lemma are the same. It's just functionally. In fact, the word def is the same, but it's just theorem considered more important. Right? Lemma just marks it as being, the supporting thing. Okay, so that's good. I'm going to make that little tiny change as well. What did I change? Just that one line, I think. Oh, and I removed a comment. Minor cleanups in PrimeSieve. Okay, so. So another. Okay, so then. So all of this is just mathematical facts given that you have some structure that does this, that implements this sieve state concept. And everything else is just follows from these definitions, right? And these facts, right? So you prove these three things, and then everything else you just get for free. So now we have to do that. And again, like, I wrote the initial implementation of this, and it didn't have any weird data structures or anything like that. Like, it was just this thing I'm calling a rake is kind of implicit in, like, well, there was a little bit like we have arithmetic sequences, which is really just, the idea that, this, you have a plus d times n, right? So it's just two pieces of data, two numbers, and then you can do some calculations on it, these little simple things. And then we name the ones that are the natural numbers and the evens and the odds, and probably should call this like nats or something like that. We have an operation where we can partition one of those into smaller, into numbers, a number of sequences. So take that sequence and divide it into n pieces, or I guess what do I call it here? Partition into n parts, and we just do n mod 0, or we give the sequence, we give the input sequences, so called n here. So we're going to turn n into a d, so it's going to be d, so it's, if n here is 5, it's going to be 5 times n plus n is going to be 5 is going to become the d, and it's going to be 5 times n plus 0, 5 times n plus 1, 5 times n plus 2, and these are all lines that form, that give you 1 out of 5 of the integers, right? Just like the odds are 1 plus 2 times n. Well, evens are 0 plus 2 times n. Well, you can do the same thing, 0, 1, 2, 3, all the way up to whatever number you divide things into. Anyway. Okay, so yeah, so a rake. Oh, sorry, we haven't even gotten to a rake. We just have a sequence, and we can filter it by being greater than or equal. We just add the, if the coefficient is less than this number you want all the numbers to be greater than or equal to, you just keep adding the delta until it gets bigger than the number, right? So that's what this does, and we can prove all this stuff. So we can say evens greater than 5, and you get this, or we can say evens 10, or just give me the first 10 terms of evens, and there they are. Now give me greater than 5, blah blah blah, same thing. So it just moves it a little further. Okay, so that's a sequence, and then, or arithmetic sequence, and then I had the main file, which is what I was saying. Using that a sequence thing, I made a PrimeSieve, and again I have to restart it. And take its time, but at the end of the day, it can iterate and produce sieves, primes. And so what it does is you start out with all the even numbers, and we get those. Right, so it starts out with, I'm sorry, it's not the even numbers. It's all the numbers greater than 2, or greater than or equal to 2. So we have 2 plus n, right? And then we're going to split that based on the number 2. We discover that 2 is the first prime, or we know it's a candidate prime. And we're going to split it into 2 pieces. So we're going to split this into 2 pieces, the evens and the odds. We discard the evens because they're multiples of 2, and we're doing a PrimeSieve, right? So we're scratching out all the multiples of 2. Leaves the odd numbers. 3 plus 2n is the odd numbers greater than 2, right? So it's 3, 5, so we drop the 1 here. And then now that we have that, we say 3 is prime, so let's get rid of the multiples of 3. So we multiply this number by 3, and we add 0 and 1. So we feed, we feed for n here, we feed in the entire sequence, 3n plus 0, 3n plus 1, 3n plus 2, and then 3n plus, well, one of those, 3n plus 0 would be is going to give you, sorry, right, it would give you 6 plus 6n, right, which is a multiple of 3, and so that the whole line gets wiped out, and then you have 5 and 7. And then over here, you keep splitting this. So you split each of these into 7, or so we have 5 is the next prime, the next candidate. We split each of these into 5 pieces. Some of those are going to be multiples of 5. It's a line that starts with the coefficient, the constant term 5, and the one that it's 5 plus 30n and 25 plus 30n. Those are both going to be multiples of 5. Those entire lines will be nothing but multiples of 5. And those are the only ones that have multiples of 5. So we cut those out, and all of these left are going to be just lines that have the same slope. And where they intersect the grid points, those are going to be integers, and so that's the arithmetic sequence. So these numbers form the arithmetic sequence of all the integers, or sorry, all the natural numbers that are greater than 2 and are not multiples of 2, 3, and 5. And then we do the same thing over and over again for 7. I mean, we look at these, figure out, well, one of these is the minimum. So it's, if you imagine these as a bunch of lines with the same slope stacked on top of each other, I call that a rake, right? And then the bottommost tine of the rake is the one that has the smallest coefficient, so it's 7. So that's the next prime. And so this is just like a different interpretation of the sieve of Eratosthenes, and it's actually like very, very slow, but in terms of an algorithm, it's not a very efficient algorithm, but I just wanted to prove that it was true. Like, it was just an arbitrary exercise. A friend of mine was showing how to do this. So I picked that as an exercise to prove in Lean for this video series. Anyway, you keep going, and it generates all the primes, and you can see that the reason it's inefficient is because it generates all these series, and at every level you're multiplying by, basically you're multiplying the number of series that you have by the next prime that you found. So this grows. I don't have a word to describe it, but at every step you're multiplying by a prime, and then you cross out. So if you multiply by 5, and however many you have, each time you multiply by 5, one of those 5 gets crossed out. So it's like you're multiplying by 4. So you're always multiplying by one less than a number. One less than a prime number. So you wind up with 2. So 2 minus 1 is 1. So it's and then 3 minus 1 is 2. So it's 2 times 4 times 6 times, I guess it'd be 11. So then 10. Right. So 2, 3, 7, 11 becomes 1, 2. 2, 3, 5, 7, 11 becomes whatever. I'm rambling. Anyway, you know how to subtract 1 from those numbers, and then you multiply the results all together, and you get this big, complicated, ever-growing number of things. And actually, I can. This is why you have J, right? Yeah, you can write it like this. Where'd J go? I don't know why I'm taking this tangent here. But whatever. I'll do it just because it's fun. So you have the first 10 primes, 10 p of I10. First 10 primes, you subtract 1, and you take the running sum of those, right? So they get huge fast, right? Huge. So if you take the first 50 of them, it's just like ridiculous. If you want to load plot, like that's what the plot looks like. it's worse than exponential, right? Because you're not just multiplying by the same number and over again, you're multiplying by a number that grows. It's worse than factorial because the gaps between the numbers are growing so fast. It's almost primordial growing. Primordial being the sum of the first 10 primes. So it just like takes off. Like it looks the same even if you do it like 10, right? Like even at 10, like it just the numbers go down, but even the first 5, right, like looks the same, right? That's just how it is. So this thing grows huge. So it's a completely unrealistic PrimeSieve. Although the point is that all of these numbers have a high probability of being prime, right? Like even though there's many of them at any given time, like the number 13, well, once you establish this, every one of these coefficients that is less than 13 squared, so 13, so less than 169, which is not all of them, but a fair amount. What's that? 169. So it's a small percentage of them, but there are still a lot of them in this list. Like, you know, it's a long list, so even though they're kind of rare in the list, anyway, all of those are prime, and then at every step, you know, it's a good chance that whatever the next prime is after 13, so what 17, that's going to be you know, 17 squared is going to be everything under that is already found, right? So right, like in other words, once you've marked out all the primes below 17, the next, you know, you've discovered that 17 is the next prime. Well, what can you multiply with it to get another compound number? The only thing you have is the prime you're looking at, so it has to be a power of 17, right? And so everything between in the sieve, every number that you're looking at in here that is between you know, that is less than 17 or 17 squared is going to be a prime number. Well, 19 is on that list, and everything less than 19 squared is going to be a prime number. So even though you have this massive blow up, you're also finding a massive number of primes very quickly. It's, you know, I guess a traditional sieve does the exact same thing without the exponential blow up. So I don't know, but this does have the advantage that it gives you these equations, lots of them that have this very rapidly growing number, so that in a few steps, if you were able to run it, which you can't run it past about 10, because it's so slow. I'll keep rambling for a minute until this actually runs. Oh, actually, that won't actually run. Oh, well, you can't do it like that, so we have to do it like 10. Yeah, I'll show you how slow this is, basically. So 5 ran in a reasonable amount of time. I think that's actually running every time. I don't think it's cached, but 10 is going to take forever. And this file is going to be huge. The output is going to be just enormous. I probably should have hidden this. In fact, let's do that. Let's stop it and hide the text here. So now it'll just print out this one line. So this tells you the delta, the slope of the lines, and then this tells you the prime it found. And so we should see 10 primes here, which should, I think, take us 29 again. And then it's going to just take a ridiculous amount of time. Part of it is because I'm using a list. I think that if I did an array, it might be a little bit faster, but mostly it's just slow. It's like a slow algorithm. Yeah, I don't know if you can see. It looks to me like my video is getting. Okay, I'm back. Okay, maybe I'm back. Okay. Gotta zoom in. All this fun stuff. Got a green screen here. And you turn on the magic background, then you there we go, and then hopefully it'll zoom my face in. Oh, I didn't never turn my light on. Lighting. All right. So you just I forgot to also post it to the Zulip chat. Okay, so yeah, so this was dangerous. I'm not gonna run this. Oh man, it's doing it again, isn't it? No, okay, we managed to not do that. So I'm just not gonna screw with that. As I said, this is a ridiculously slow algorithm, not slow, but it has a massive memory requirement. So, and I think it's allocating and deallocating memory and just running it live in Lean is just not terribly useful. And then also at the moment, I can't like somehow lost the ability to compile an exe file, so I can't actually run it from the command line either. I don't know what's up with that because that was working fine, and then suddenly it stopped working. So I have some issue with my Lean setup, but it runs fine interactively as long as you don't let it blow up. So yeah, my thought was to that maybe this algorithm would be kind of like mathematically convenient, right? Like we can talk about it as if we had like a supercomputer that could run this program, right? Even though the program itself is like completely inefficient, the algorithm works and it has certain properties that might or might not make it interesting to reason about, in a mathematical context. I don't know. Like the point is, you don't have to actually run the sieve, right? Like according to the PrimeSieve class here, like anything that is a prime, like a sieve state, could be used as a way of making arguments about prime numbers and about sieves and so on. So if you had like if you had an algorithm that was impractical but you could describe it, and then yet it had some like mathematical property that made it easy to write the proof you wanted to write, then like it doesn't really matter if you actually if you could actually run the program or not. Like many mathematical proofs deal with numbers that you would never actually write out by hand. Like if you like multiplying some gigantic number by some other gigantic number, it's like, well, specific numbers you could do it. Like you could multiply those numbers together and get like but you don't have to, right? And even though it's intractable, intractable to actually do the thing, you can still reason about it. And so like one of the properties of this is that, I don't know, like to me it has a direct correspondence to like an actual construction of this set of numbers that are co-prime to the first n primes, right? So I don't know. And the entire infinite set, whereas with a normal prime sieve, you like the normal sieve of Eratosthenes, you allocate, you state, I want to generate all primes up to 10 million or whatever. So you generate 10 million, or I guess more like, you can estimate how many primes there are. It's like log of 10 million over 10 million, I guess. But the point is that you guess how many primes there's likely to be. Oh no, actually you would have to have a bit for every single one of those, right? So you would have like 10 megabytes of a bit, or well, divided by 8, so somewhere around 2 or 3 megabytes of data, and every one of those bits would be whether or not a prime number exists. But even then, you tend to, well, it doesn't matter. You can actually, most primes have actually used the exact trick that I'm using, to it so happens that when you do the first 3 numbers, 2, 3, and 5, once you do that, you're multiplying by 30. Let's put these back in. Right. You run this, and you get, so the sequence was oh, I lost it because I rebooted, right? But the sequence is 2 times 4. So 2, 3, and 5 give you 1 times 2 times 4, because you subtract 1 from each one and multiply it. It gives you 8 terms, that are in your sieve, right? So you have 8 sequences that you're tracking, and then you multiply by 10, you get 80. But at the step where you're doing 8 of them, well, you have you can compress the number of bits that you need to just 8 bits to track all of the numbers in these. Like, what am I trying to say? I'm rambling. I feel like Joe Biden here. It's because I haven't thought this out. I don't know what I am trying to say, so maybe I should go a little slower. When you remove the numbers that are multiples of 2 and 3 and 5, you wind up, for every 30 numbers, you wind up removing all but 8 of them. And so you can have 8 slots in your sieve, or 8 bits in your sieve, that correspond to whether a number is prime or not. And you only have to look at those 8 lines, right? So in fact, this algorithm, this ridiculously slow algorithm, can actually be used to generate what's called a wheel, right? So you describe the set of numbers that are already scratched out. So you remove them, and then you only have slots. You only write the numbers that are right, that are multiples of, that are not multiples of the primes you've scratched out, right? And then at that point, you go back. You could revert to a sieve, a traditional sieve, and you would have a massive compression amount. So there's some diminishing returns there. But as I said, like once you mark out the first 3, 2, 3, and 5, then you're moving for every 8 bits that you look at. Those 8 bits correspond to a movement, a range of 30 numbers, which I can show as soon as it actually runs this thing, which it's not running. So I don't know why. Probably because it started to run the 10. Oh, maybe I should kill the server just in case. Let's restart the server. I think it might have actually started running that, and maybe it's running it in a thread, or it's because I can see it's already slowing down again. It actually sucks. It really sucks. Okay, here we go. We're back up. I think maybe. It says loading. Should say bit. I see I lost my camera again. Hello, testing, 1, 2, 3. That happened the last time I restarted. I don't know why that would have anything whatsoever to do with OBS, but apparently it does. Okay. I'm just sitting here. I don't even know if anyone's hearing this. Wow. No, it says I'm broadcasting. Okay, so let's try this again. While it's doing that, I'm going to try and fix my camera one more time. It may not work. If it doesn't work, I'll just turn the camera off. I don't need a camera. There we go. Okay. Okay. All right, so yeah, so the server is restarted. Everything is going again. I think, yeah, it's loading. So I think this is just old. So in a minute, this should. I don't usually have these problems. It just I had left. The thing that crashed my computer was on that line. The cursor was on that line. So as soon as Lean started up, it tried to crash the computer again by evaluating 10 iterations of this sieve. That was a problem. Yeah, it just, this is a mathematically sound, but practically completely inefficient sieve. Or I guess you would say it's a it's a big data thing, right? It's not like a small thing. It's and even this like come on. Maybe I'm gonna click this restart file. I mean, it says it. Oh, come on. Technical difficulty. What I'm thinking of doing is rather than so because it generates a huge number of primes, or it generates a huge number of sequences, and all the lowest terms, or the lowest terms of most of those sequences, are already prime. Rather than having an iteration be just immediately multiply by that number, what I might do uh, is stick all those primes that it finds into a queue, and so that most iterations would just be pop the next number out of the queue and return that. But that would require a separate proof, like that the queue is working, and that it's sorted, and that every item in the queue is a consecutive prime, which might not be too bad. But it's a different proof than the main thing I'm proving. This is just taking forever. Come on. Refresh this. You see what's happening here. Stopping server timed out. Oh, so the server never stopped. Let's try it again. Let's clear this. I didn't need a terminal. Let's see what Lean is doing. Even so it's baked into the type of my RakeSieve here. The whole idea of a rake is that every uh, sequence in the rake has the same slope, so you have to generate them all at once. And I might have to change that because otherwise, because to do it lazily, they might not have the same type. Or I guess, I don't know, like I'm picturing it like kind of having like a hang on just one second. Lean is doing this. Let's see how much memory something is taking. So Lean is, I've got two versions of Lean. This is taking up almost a gigabyte, and this one is taking up. I think this is the old one, right? I'm gonna guess that this is the new one I just launched, and this is the old one, and I'm gonna kill this. And I lost everything called Lean, didn't I? Okay, but at least that one is gone. So I think that this should, yeah. So restart Lean server. Didn't. I don't usually have this problem. So it's only because I ran that. I ran the 10 iterations, and then when I rebooted it was on that same line, and so it tried to run 10 iterations again, and that's the problem. This seems like it's already, yeah. So this is what I'm used to. This is the kind of speed I'm used to. You see, it's all those yellow lines went away. It's all good now. And if you click around, you see it's got. I'm getting live output, so that was it. Okay. So what I wanted to say was that if you look at this, you see there are 8 terms here. So these are all the numbers that are not, like every natural number greater than 2 that is not a multiple of 2, 3, or 5 is going to be on one of these sequences. And there are 8 of them. And so when you write your PrimeSieve, rather than having a bit for every number, where you would have 30 bits, you can just have 8 bits, and so you've got a byte, and that's how the so you have 1 byte that corresponds to a slot for each one of these things. Whereas if you do it here, you can do 26 at a time if you add in 7, and then after that, am I wrong? It's 48. All right, so you could do this with a 64-bit number. You could do up to number 11. So you could filter out 7 and 11. Oh no, this would just be 7, and then it would see. So if you filter out 7, then the next number you're looking at is 11. But you'd have these 210. For every 210 numbers that you would look at, you only have to look at 48, and that fits into a 64-bit integer. So that would be one thing that you could generate with this. You could generate a regular PrimeSieve using this setup, and then here you could do it. So it's 480 sequences. So you could break that into a 512-bit block or something like that to be aligned well. I don't know. Okay, well, that's for another day. I don't know that I'm ever even going to implement that. It's an optimization that occurs to me. It's not something I'm trying to do for my video. So all of that was just a huge waste of time as far as I'm concerned. I'm an hour and a half into this now. But let's go. All right, so I talked earlier about the PrimeSieve concept. So I have a generic PrimeSieve, and now on the other side, I've got an actual implementation. So I've got the generic thing, and that has a proof now. And I have the generic, the specific thing, the actual implementation of something. That's this rake stuff. And I have a rake map that can model the idea of all these numbers and say, the set of numbers greater than, or the set of natural numbers greater than a number, and without certain primes. And then by sort of like induction, you can build up step by step the set that corresponds to the uncrossed out numbers. So, yeah. So we have a sieve, RakeSieve, and the goal is to implement PrimeSieve, and to do that, we have to show these 3 things. That so in the land of PrimeSieves, we have this notion of a set called S and R. So S is just the set of primes that are greater or less than or equal to the current prime that you're looking at, or the highest known prime. And then from that, you can derive the set. You're going to choose C to be the smallest number of this set. So C has to be an element of R. So this says for every number greater than 2, if there is a prime that we know about, so a prime in S of X, X being the state, then that prime does not divide n. So n being any number. So the set R is defined as all the n's where n is greater than 2, and no prime that we know about divides that n. Or it does. For all of these primes, it does not divide them. So all the primes that we know about do not divide that thing. That's how you say it. So we have to show that C is an element of that, and that for every element in this set, C is less than or equal to it. So these are two kind of complementary things. And then we say one is the thing we find is higher than the other one. This kind of I think maybe you could prove this. I think this could probably be proven from the definition of R and the definition of S. In fact, I bet it could be. But maybe start with that. Because if we prove it here, we don't have to prove it for, again, I'm imagining like I'm in a sieve factory where I'm building lots of sieves, right? And it's not necessary to do that. I could prove it over here or I could prove it over there. But I think it follows from the definition of this, right? So the question is, where is this used? Go to references. Is this used at all? So we have here. If I prove this separately, I mean, I just kind of like made up the condition here that this is. And then here it's I'm using it inside of the proof that C is prime, right? I think I should only need these two things. This is kind of a weak statement anyway. Let's see if we can get rid of it. That'll be a good opening exercise. So let's prove right here. Let's prove theorem C greater than P for a type, and I guess we'll put these conditions here. So this says that we're talking about a sieve state. So some type that somebody implemented, me probably, that implements this. That if you implement this protocol, and this, which is PrimeSieve, just copy it from down here. And I'm calling it G because it was a generator, but we, I just call it X maybe. Then, so if you have these things, and you only have to supply a type, so C, this is going to be true of anything that is a sieve state. That what do we want to say? That C of X is this thing. I want this is greater than P of X. I'll call it G for consistency here. Yeah. Okay. And then so we have to prove that. By. And I'll just put this all in one line because blah, blah, blah. All right. And then if we put an underscore here, it'll tell us what we have to prove. So we have to prove this. Which is good because that's what we said we were going to do. All right, so how do we know that? What's my argument for knowing that? I always want to try stating it in English first. Well, I mean, it kind of follows from like from this, right? That and I might eventually change this to not even use sieve state at all. So this we can just not, we don't even need a PrimeSieve here. We can just talk about sieve state, right? That if you have a sieve state, then for all so for all elements of R, R is greater than PG. Right? What's wrong with that? What's wrong with that? What does it say? Membership. Set of NAT. So what? Failed to synthesize membership. Use set option. Or we just do this. Probably the same thing, right? Maybe we have to have this. No. Oh, no. Oh, I have to give it G. So this. So this is the proof. Do I have auto implicit turned off? So I can't just use a name like this because auto implicit is off. If I comment this out, that would work fine. It should work fine. Yeah, see now, well, no. Yeah, now it went away. The red lines went away after the yellow stuff went away. But with this on, that triggers this, it'll trigger a problem. Get the words over here. And once this goes away, that'll turn red. So we'll say for all, we have to introduce this variable. All R. There we go. I don't think we need the .val. We might need this. What's happening now? Sometimes this happens, and this is just wrong. This is, I think this is right. Nope, it's because this is there. There we go. Okay. But sometimes a perfectly valid statement does have a squiggly line, and I don't see why, and I have to restart it, and then it just works. And I don't know why. It's just a glitch in the IDE or the language server or something. Okay, so we have to prove that this. So we can intro R. Now we have an R that's a natural number, and we can even say R. We can say HR in R. I'm just call it HRR, which is this. R is element of R. And now I have to prove that R is an element of P. And so we can try to use automation to prove that. All right, so we could also say no, that didn't prove anything. That didn't change anything. What's my argument? So the argument is R, or rather S includes every prime less than argument. Prime less than or equal to P is in R. So somewhere down here, I already have a proof that no prime factors implies no factors. This does not depend on anything having to do with sieves. I could move this up. I think I might need this. But it might be the opposite statement of this. Let's see. P is less than C. I think I can prove this by contradiction from this lemma. So if I move this up here, move this here, up to the top, and you can see it says, so if given some number C, if you have all the primes less than C, right? So if it's a prime and it's less than C, then it won't divide C. And if you had any number, I don't know if it's going to be the exact same thing, but some of these facts might be similar, right? So the idea is that so if a prime is less than P, then it's in R. No, sorry, S. So and so S says R and S together. R and S together say for all P prime less than P, not P R. P does not divide R. Okay. That's that. I mean, that's just the statement. But then, what's the argument? The argument is so we're going to say it's going to be by contradiction, right? So we have the so that there's not R is okay. We're going to simplify. So we're going to call this the call it H. The hypothesis H, and then we're going to simp H. Simp at H to get less than or equal. So R is less. so some little r in the set is less than or equal to prime, to p of g. Okay. So we want to say have f is a factor. So one of these. I think this. Yeah. So I want basically this. So let's. Okay. Let's unfold R and S at HRR. So we get this nice thing. Okay. And we can actually move this up here, so it's first thing we do. So we unfold that. I guess. We should be able to show a contradiction based on if R is less than or equal to P, there is a contradiction. Because what is the argument that there's a contradiction? Well, actually, we can say there is a contradiction one way or the other. One of two ways. We're going to say proof is by cases. And the cases are by cases contradiction in one of two ways. By cases, and we're going to say H RP, that H is, or how about literally use a apostrophe to say nat prime of R. So if, so we say case pos, so if R is prime, then something, and then case neg, sorry. And I think if it's not prime, we have a contradiction, and that's something to do with this thing here. So I'll put the sorry down here, and we're actually going to be talking about some number R that is not equal to 1, which I don't think we have. Can you even say this? Like, this is like a direct quote. So you'd actually want to say it like this, and that is, we should be able to prove this by ASOP. Yeah, it should just know that. Something in here, like it says n is greater than 2. So from here, probably by HR, we can actually see how it did it, and it's some messy thing, right? And there's probably a simpler way to do it, but whatever. All right. We can actually even call it this or whatever. But all right, so that we'll fill in later. What's the case if it's prime? Case pause. So R is prime. I think ESOP can figure this out. Just say ESOP. No, okay. At prime R. And R is an element of this set. So let's apply. How do we get this? How do we get this statement out? We just ask for it, right? So we'll say have R actually, so let's say HR. We'll just say HRR dot right. Right. So the right. I took a guess, and it this would be the left, and this would be the right. So I got this thing. So we move this. I just made a copy of this little part of this thing so that it's easier to see. P divides R. So we can say have not P divides R. Oh, well, that's, wait, hang on, that's clear because it's prime. Oh, right. Well, we really want to say, so given this, call P, if P is prime, and it's less than this, so we're saying R is less than this. So we're going to derive the statement that R does not divide R. That's how we're going to get that. That's how I'm going to do this. So let's, we say specialize this with R. No, hang on. For all P. So specialize this with just some letter P, or we'll call it Q. But that didn't work. Specialize with H with Q. What's the so let's see what specialize says. How do you do specialize? Specialize H on local promises. Okay, I'm using the wrong word here. So I have a cheat sheet somewhere. That Kevin Buzzard made for his class on proving E. Where is it? Oh, don't tell me I lost that. Oh, here it is. All right, so oh, maybe I have to show this, right? So I'm doing it right, but I have to show this. So so R is an element. So R is less. So right, so I have to prove this by contradiction. So by contra, right? Now, so we'll call this H that R is less than P. R less than or equal to P. RLEP. Okay, so now we have this thing. Let's see, simp at RLEP. HRLEP. I'm just going to call it, I'm not going to do that, capitals RLEP. Simp at RLEP. So hypothesis that R is less than or equal to P. And we're going to say, now we can apply that to this. In fact, I think we can derive this directly. So we would say have not P, not R divides R. ESOP by ESOP. Try it again. Typo there. Can't do it. Oh, I can't do that yet. All right. So there might be some tactic out there that can do this, but we can actually ask for that. We can say apply question mark. We use anything to derive that. How about exact? So nothing exact proves that. Nothing rewrite proves that. Ooh, rewrite proves it. No. Okay. It didn't prove it. It just that list made all those things made it advancements. So there's something that can be applied, but they don't necessarily do anything useful. Maybe if I read that more carefully, there would be something. I'm trying to say that for all P, and I have this, so P is less than this, R is less than that. So if I have R prime, so R is a prime. So I think we can apply this. So now we can say with R. Sorry, with, hang on, wait. I think, no, it's not a specialization because we're not just introducing a variable, we're actually using a specific variable. A specialized introduces a new variable. So what we want to say is, I think we want to apply this, apply H at RLEP. At HRLEP. All right, so then we have to say that from this we can deduce this, right? can say R in that. R is in that. Sorry, R. What's wrong with this? What's wrong with that? Is that it's R is a set of nats? Yes, R is a set of nats. So we say R.val. Oh, R is a nat. Okay, R is a nat. R is a nat. Oh, HR. So maybe we say R. Oh, we say, okay, so you say, this is just normal. You say set R, let R equals n prime, R of type n prime is equal to R, and you have to provide a proof. So you say equal to R with the proof that we already have here, which is HR prime. Right, so now we have this actual variable here that R is n prime, and then we can use that. R prime is element of the set. Sorry, and ESOP should be able to figure this out. ESOP. Yeah. Okay. And then now this follows. And then we would say there's got to be something on something that does this, and I think ESOP does it. Yeah, it proves it, but let's find out how it proves it. Ah, come on. Is there simp? No, there's exact something. So if you ask for exact, this is a lemma. No way. There's got to be something there. So there's got to be help hack help term. This is new to me. Nat div nat divide well, okay. This should just be R divides R by this is exact somewhere. There we go. I figured this would exist. And we don't even have to say by exact. This is just a function application, right? Whatever this is, this takes an argument and produces a theorem, right? So it says given an A, it produces a value of this type. It's a proof that A divides A, whatever it is. And this is a contradiction. And that's it. So we didn't even need this little thing. We need our prime to. Do we need this? No, not really. This is an unnecessary step. It's just easier to see when you're paging through it. Okay, so that's the proof. So that's the proof that if R is prime, we have a contradiction here. So that closes the goal. Basically, when R is prime, we've proven that that this is true. That R is that sorry. Right, when so we introduce some R in the set R, and then we've proven that it's greater than P, because R is defined in terms of P. All right, and then from this we're gonna be able to easily demonstrate that this specific C, which is a member of the set R, is going to be right, because it follows from this. From this, we're going to be able to show this by this lemma that I'm proving right now. Okay, so that means where are we at next? Case negative by contra simp at H. We have this because R is not. From all this, we can say R is an element of the set. We can see it's greater than 2. Everything in R is greater than or equal to 2. So I'm going to introduce, since R is not prime, it must have a prime factor. Yeah. So F is a factor and F divides R. So say HF prime, and then I think FR is that F is a factor of R. So once we've done this, right, now we have these 3 new things. You can see it's in green there, so it's indicating that we have 3 new features. Or F is a natural number, F is prime, and F divides R with these 3 names. Okay, it must have a prime factor F. Have F is less. F is less than R by ESOP. Oh, can't prove that. No. F is less than R by. Why would I believe F is less than R? What do I know about F? Because it divides R. How about less than or equal to R? No, can't prove that either. I think omega is, this tells you like a possible thing, but is this true? Am I saying the right thing? Sorry. Let's see. Why do I think that? So let's again put it into surely that's true. nat, let's see, term, help, term nat, LE of divide maybe? Let's say print this. If 0 is less than n, right, so we have 0 is less than f, because it's prime. What? Looks like it found something? Yeah. So we hit control dot. Oh. Yeah. So it found it for me. Right now, still doesn't find it. What is wrong with this? Print that out again. Let's see what's going on here. And m divides this, so and HFR. FR is this expression. What's it mad about? Well, it wants R is greater than 0. Okay, so we have HR prime then. R prime. Oh, R is not prime. Okay, hang on. Well, okay. R is greater than 2. So we R greater than even 2. I think we have this. We don't have it explicitly, but I thought we could derive it from this. Let's say, oh, but it's not. That's not what it wants. It wants a have R is greater than 0 is less than R equals HRR left, right? Why not? What's on here, left and right? Okay, that's true. Now we can say have R has 0 less than R equals exact something, right? Oh, by exact. And we probably say HRR left directly. So we don't need that. Okay, so now we say this here and HFR, and so now we have F is less than or equal to R. And F is prime. And R is less than P. Okay, so now we should be able to say have F is less than P equals by ASOP. By trans. Nope, trans by rel. This. Is that true? Oh, okay, that worked. That was good. No. That seems wrong. Omega should be able to solve. Okay. You just have to try different things to see if they can solve it. Like ESOP, Omega, Linarith, all these things. You just kind of get a feel for it. Linarith should be able to solve it. Nope. Omega can solve it. Okay. All right, so now, no. Wait, what? Why does it have a sorry term in here? Oh, okay. I see what I want to do. Can we calculate? Maybe we can calculate on this. Calc F is less than R equals N. Okay, so F is less than. Okay, so we have F is less than or equal to R. And we have R is less than or equal. Oh, so we can only say it's less than or equal to PG. Yeah, no? Yeah. And then from this, how do we show that R is in there? we want to show this again. So this kind of step, but for f now. And f is prime. So HF so we say let HF, there's got to be a better way to do this. I mean, I made up n prime, right? So maybe the answer is that you just don't normally make up this wrapper type, and then some of the problems go away. But I'm kind of used to it now. So so we say HF n prime is that, and so now we can say, sorry, we say f prime this, and now we have that. Then from this we can conclude. So from a chain of relations, we can conclude that f is an element, or f is less than or equal to p, p of x or p of g, which means that R cannot, that it can't divide anything in R. By the definition of R, but the definition of R says primes less than or equal to p can't divide, won't divide R. So now we have contradiction, but I don't think you can find it yet. All right, so it's the same line here. Not f divides R equals by ESOP. Proof is same as above for above when R was prime. I don't even think we need the negative case. I don't think we need the positive case. This is all one case. I might undo that. How do we get R as this? Okay. There's a contradiction. So R must have all R, like all natural numbers, has a minimum prime factor. From and then we also have actually it's probably like HFR. HFR, right? F divides R. It's already a contradiction. Can you give a contradiction a... You don't say what it's supposed to. Okay, and that concludes the proof. So we don't need the same as above. Because it was same as above, we just consolidated. All right, so we did the same logic on both sides and consolidated it. Anyway, that's the proof. So everything in R is greater than P. We use this to show C is greater than P later. What's this mad about? I don't know what happened there, why it was all weird like that. But it seems to be good now. Okay, what's wrong with this? Where does it use sorry? See, this is a lie. Right, restart the file. Okay. I feel like I'm starting to get the hang of this, you know? And now this should be... and now we don't need this. So, as soon as I delete this, right, it's gonna complain. I could go to references, peek at references. So we'll just replace this every time we see it with CDTP. Oops. C greater than P. Oh, it didn't like that. Oh, I have to give it alpha. Yeah. Is that it? That worked? It didn't turn blue. There's like two phases of the syntax highlighting, so sometimes it doesn't work. But that seems to. That seems to have worked. Okay. And in fact, we don't even say bye. We just leave it there. Okay, so now we can get rid of this one. Oh no, there were still two uses. I'm just gonna get rid of it. It's gonna put a red line in here somewhere, and then I can just jump to the red line. Oh, okay. So what it found was it found this proof, but I want a different proof. Right, so try that again. Yeah, I didn't read that carefully. I tend to not do that. All right, so why should I believe this is the case? Because of HC and R. So we say by have, and we just introduce e.hc in R. Little thing there. What's going on? I guess I have to say prime sieve hg and rg. Yeah. All right, so now we have this thing, and now we should be able to say exact, and it should be able to find, yeah. And that's the end of the proof. And then we say cgtp. Or you can say alpha here. Oh. Okay. So all this works. It says it's proven. You would think that if I'm just going to roll this back for a second. Oh, I see. I'm expecting something to go wrong here, but it doesn't. It just shows this. You would think this would fail, though, right? Yeah. C greater than P. Okay, that's it. All right, so that was a whole lot of work, but we accomplished PrimeSieve, eliminate need for HC greater than P. Right? I wound up not using this. So I could put this back here. Put this back. If I do this, if I undo this, it's locked. It's locked because it's a stage change, right? Let's undo that. Now go here. And put this back. So back over here. And then here where we said no prime factor, we didn't use that up there. I thought I was going to have to use it. But instead I just used a similar proof with this obtain thing that obtains the prime factor. This prime and divide. And then we got rid of H. Just triple check that that still proves. Close the diff, go back here. Make sure that everything looks good, looks good to me. Where's my info view? Responsive, it says no errors. We're good. See this dark orange or yellowish color is indicating that it's got a problem in it. Whereas this color just indicates it's modified. They're kind of similar colors. All right, so that's what we did. Okay, so that reduced the amount of work we have to do here. Probably would not have been much work at all to prove that the number that we're generating here is much bigger than the other one, but we don't have to need that anymore. So if I restart, in fact, let's undo that. We restart this file, and now it should tell me that this is not a recognized thing. Yeah. It doesn't know what that is. So we get rid of it, and then we get rid of it. And so now we're down to two things we have to prove in the RakeSieve implementation. And they're very similar. But there's nothing to prove yet because I haven't implemented it. Or have I? All right, so yeah, this is the line to prove. So right now I just say C is just the next number, so this is not a correct implementation. But maybe I'll pick this up tomorrow. It is like almost 4 o'clock in the morning here. And while I have been working late, I should not be up this late. So here is where I was talking about finding a keeping a queue of all the, everything up to the square of every prime we found. And maybe do that before we start exploding the number of terms. You can scrape a lot of these things. I'm just thinking about how the sieve works, because I think I originally called this repository TreeSieve because I was going to use it for a tree of these of arithmetic sequences, and I guess now I'm starting to picture a rake as being a node in that tree, right? So you would call it a twig, right? Like the leaves of the tree are the arithmetic sequences themselves. A rake would be right above the leaves, so that's we call that I call it a twig. It's called a twig in the Neal programming language. There's a word called twig. Gives you right above the leaves, and then everything else in the tree would be like so it would be a tree of rakes where each rake had its own what am I trying to say? The defining feature of a rake is that it's a collection of arithmetic sequences that have the same delta, so the same slope of the line. And what I'm kind of picturing now is that you'd have a tree of these rakes, and some of them would have different deltas. So you rather than having this multiplicative explosion, what you would do like it's cyclic, right? So we go back here. I'm just going to ramble a bit. This is I'm done for the night proving stuff. I'm going to come back and work on the implementation. But I'm just kind of like thinking ahead. Like this is kind of cool, and this is something I think might be interesting to make if I have time to do it this summer. And I think I do. But I'll probably work on my animations first. But I just want to talk it out. Right? So you keep splitting these lines, and now you have this is what I think of as the the rake. But like 7, we determine at this step that 7 is prime, right? And this is our candidate prime, and the PrimeSieve class takes this number C and says provides a proof that this is prime. And so in this printout we have this thing called H. H is just C squared. So here it's 25. Everything that you see, all these numbers are less than 25. So they're both prime. And then here we've stripped out the multiples of 5. So anything less than 49 is prime. So they're all less than 49. But then we multiply all these by 7. So 30. I'm sorry. We multiply the 30 by 7. And we multiply all of these by 7. And so now we have a bunch of numbers that are more than 121, which is the square of the next prime, right? So, right. So we take this sequence and we apply it to the sequences 0 plus 7n, 1 plus 7n, 2 plus 7n, all the way up to 6 plus 7n. And that partitions the natural number line, the natural numbers into groups of 7 equivalence classes. And then we use those equivalence classes to partition each one of these lines. And so that's how we multiply by 6 here. We multiply by 7, but then of those 7, one of each of them is going to be a multiple of 7. Right? It's going to produce nothing but multiples of 7, and so we scratch that out. And so we wind up multiplying this number 8 times 6, and we wind up with 48 new sequences. So of these 48 sequences, though, you know, they all have the same slope, but the first term of each sequence is gonna you know. So all these 48 sequences together give us all the numbers that have not been scratched out of our sieve, right? So whatever the minimum number is prime. And since they all have the same slope, the minimum number in the set is whichever one of these constant terms has the smallest value. So we should sort this list, and it's going to wind up being 11, right? So 11 is the smallest one, right? So then, also though, like we already knew all of these numbers were prime, and because we multiplied by, you know, we applied it to the sequence 0 plus 7n is one of the things we did. Then every one of these carried over to the next set. So it's, you know, because 11 plus 30 times 0 plus 7n is 30 times 7, which is 210 plus 11, right? So that's how this got preserved. But in addition to that, we also said 1 times 7 plus 11 times, no, plus, well, oh, I see, this would be, no. We think, oh, I see, 1 times 30, you know, so we said 1 times 7, so we applied this thing right here, and for the n we filled in 1, instead of n we replaced the n with 1, the entire number line, 1 plus 7n, and so that gives us 11 plus 30 times 1 plus 30 times 7n, and so it's 11 plus 30 plus 210n, and so that's 41. So, and then this is, you know, this is after we apply 2n. If we apply this to 2 plus 7n, and we get this, and 3 plus 7n gives us this, 4 plus 7n gives us this, 5 plus 7n gives us this, 6 plus one of these looks like the big gap goes from adding 30, this is adding 30, this is adding 30, so you see there's no 161, and that is because 161 must be a multiple of 7. It has to be. If it isn't, then things are wrong. So if we say what are the factors of 161, yeah, 7 times 23 is 161. So so that's why that's missing. So that got filtered out. And then here we're doing the same thing with 17, and you can see there's a gap between 47 and 107. So that number 77 should be a multiple of 17. No, it's a multiple of 7. Okay, right, a multiple of 7. All of them are going to have some multiple of 7, which of course 70. Yeah, right. 77 is a multiple of 7, obviously. And then same thing here. When it gets small again, then so it got small 23. We had 30. It looks like what did I miss? When is it? We had 23, 53, plus 30 plus 30 plus 30 plus 30. So 203 must be a multiple of 7 as well. Yeah. And so on. And so that line got marked out. And in fact, everything on that line, because it's you know, if we're saying 203 plus 210n, well, if we factor both of those numbers, oops, right, they both have the number 7 in them. So it's 7. We divide this, right? So it's 7 times 29 plus 30n, right? Which is how we got it, right? 20, we took 7 and right? that sequence is always going to be prime, because you've got a multiple of 7 plus a multiple of 7 over here. A multiple of 7 plus a multiple of 7 times some n, right? It's always going to be multiple of 7. 2 multiples of 7 added together is another multiple of 7, and so that whole line gets wiped out. Anyway, that's the principle. Well, where was I going with this? I was going to say that right now we sort this, and because we're just taking 1 out of every 7 numbers, moving them to a new line, 1 out of every 7 numbers, moving to a new line, and just dividing the lines up into little, like basically chopping the whole sequence into chunks of length 7, and then rearranging those sequences. They're still in order, and so we can look at these and say, well, once we sort them, right, we can say anything that's less than 121 is prime. So let's just add that to the queue. And then later on, when we're done with that, we can just imagine that we multiplied it and gone on to the next group of numbers. But like, we don't have to multiply something out until we what am I trying to say? Basically, that I think we can dynamically sort these things in such a way that, like, it preserves what am I trying to say? I think we can treat this as a queue and not do this blow up until we absolutely need it. And like we put it in a heap and just treat them as counters. And so as long as the counter you're looking at like as long as the topmost counter on the heap, like the priority queue, is you know, we would know it. Like if we know it's less than a prime that we've already found, or rather less than the square of a prime that we've already found, then we just keep going, right? What we do is we look at it, we say we add it to the queue of primes, which is just a list of integers, list of natural numbers that are primes that we found. We could just add the sequence to that queue. So like anything that where the constant term is a prime, we just add it to the queue. I'm trying to think how to do this without having some redundancy, but basically you just keep going. I can kind of visualize this. The idea is to introduce this notion of a queue, right? This queue, this queue right here, which I would call Q, of course. And it would contain, but it probably wouldn't be just an array of gnats, but maybe an array of rakes, right? Array of rake map or something. And like the idea is that each step we generate a bunch of primes because everything up to the C that we generate, everything up to C squared is actually prime. We filtered out everything. The C squared is the next possible number, the compound number. Anything less than that is prime. And so we don't have to just, in order to find like a bunch of primes, we don't have to do any kind of this multiplicative blow up, right? That's the idea. That's the idea I'm getting at. That at every step, each prime we identify pushes the horizon further, and we can delay this blow up. Obviously you don't need to do it at all for a sieve, right? I'm just thinking there's got to be some. I think maybe you could even construct something, right? Something that would track the to-do list, right? See, the idea is that eventually in this model of the numbers, you do have to do that multiplication, but maybe you don't have to do it right away. I don't know. Now I'm starting to think. I'm almost wondering if you could use like a different kind of sieve to generate the terms of the sieve, to generate the terms of your sequences. I don't know. I mean, like this is no longer, well, okay, I see the flaw immediately, right? this is not an arithmetic sequence. Like, what sequence generates this? Well, a list of prime numbers, right? If you knew how the primes were arranged, then like you have a Fields medal, right? You'd have to like prove the Riemann hypothesis. But if you had a list of primes, like maybe you could combine that with maybe you could reuse that list in another way to shrink this down or something. I don't know. I'm not really sure. I don't know where I'm going. Recalculate it on the fly or something. I mean, again, you could use a traditional like bitmap sieve with these filters applied to compactly store the list of primes that you've generated using this compression method where where here you got for every 30 numbers that you would have, you can use so in other words, you can use 1 bit per number, and for every 30 bits that you would have if you just enumerated all the numbers, you get it down to 8. And here, for every 64 that you have, sorry, for every 210 that you have, you can only use 48 bits. Right? And so from this representation here, for every 2000, you only use 480, 2300. And for these, there's kind of diminishing returns here. But maybe you're somewhere around this point, right? You could just have like a bitmap that was just 1 bit per. I think that's as far as it goes. As far as I went with that run, but like you could store this table of these numbers as bitmaps, and then the bitmaps themselves could be interpreted according to this rule, kind of recursively. And so you would have a tree of these things, right? Like this would also be a rake. Is it a rake? Well, it would be something like a rake, but it would be a very compact, bitmap representation of a rake, right? So at this level, the rake, would be, because whatever your delta is, you have the number 30, so that's your delta, and then you'd have 30 bits that where 8 of them were set, and then here you would have the number 210, which is your delta, and then you would have 48. I'm sorry, you'd have 210. Sorry. Yeah, you have the number 210 bits. Of those, 48 would be set, and from that you could derive what these, the positions of those 48 1 bits would tell you what these 210 numbers would be. So you could store this entire rake that is currently taking up all this massive amount. I mean, it's just this number, two numbers so 2 numbers times 210, so 420 numbers are being stored. Each one is a big integer, and you could store it in 210 bytes or bits, right? Plus a length bit, so very, very small. Same thing here. And again, there's some diminishing returns here, but a little table like this would be very fast to consult, and you could kind of recursively use several of them at a time to calculate the numbers that you want to calculate. I don't know what the point of this is. I guess part of the point is that it's a continuously accelerating PrimeSieve, right? It's diminishing returns, but it accelerates at every step. I don't know if there's a value to that or not, right? I don't know. I was, the person who brought this to my attention, it wants to do some work with like the twin prime conjecture and stuff, and I couldn't, I don't see an application, right? I mean, you do. The idea is that you do see that there are pairs, right, at every step, and like, if you look at the list of things that are in your queue, right, the things that you've shown to be prime, but are not yet prime, not yet marked as prime, then if you could show that you have this queue of numbers and there's a bunch of pairs in them, and the queue is growing at a certain rate, you do this operation where you multiply the number of pairs, by a big number, by a prime that you found, and then the pairs that existed, in your sequences, that you do enough of them that maybe you could show that something, about like the rate at which they disappear, like so if you have a pair of sequences and one of them gets canceled out, and now you have like a singleton, right? They're no longer paired. So forever on, those two lines will never produce a pair of primes because they're not, a twin prime, because they're not separated by a width of two, right? Uh, so whenever one of them drops out, that's that would prevent them from making primes ever again, or their descendants from ever making twin primes. And but anyway, the goal, the twin prime conjecture would be that there's always a pair that are two together, and that you know when they get admitted um, into the queue, because the prime that you just found is, they're less than the square, they're less than the square of the prime that you just found, then maybe that would show something about the twin prime conjecture. I don't think so. I think that's very unlikely. Like even just talking it out, it's uh, like it's just very fuzzy, right? But I think you could maybe make some statements, and I tried to find anything that we know for sure to be true. I don't know anything about that. Um, I tried to make some statements about like how is the queue growing and that kind of thing, and I didn't see anything really useful. But that was the idea of this sieve in the first place, is that you could modify it to track pairs of lines in the rake that are separate, for any tuple or whatever, separated by two, separated by whatever, and as long as you're as long as you keep making copies that are separated by the same distance, which you do when you use this partitioning procedure, you always have these lines. And there is a proof that if you have such a line, and the number, an arithmetic sequence, you have an arithmetic sequence, and the constant term and the delta are co-prime, which all of these are by definition, by construction, then each one of those lines will have an infinite number of primes on them. But there's no guarantee that they yet, right? If the twin prime conjecture were true, then you would, for any pair of lines, you would likely expect to see an infinite number of places where both of them, were term like x of that sequence was prime, or you would see term x of both sequences would be prime. So it's always prime, or there would be an infinite number of places where both sequences produced a prime, and descendants of that sequence, whatever, or just even just that one sequence. Those two sequences, they're kind of parallel lines. They're going from the origin off into at some ridiculously high slope, because the slope was a primorial. You would see an infinite number of primes on both of them. All that's true so far. And then the twin prime conjecture is that, I don't even know if you would prove that, but like there are at least some lines, some pairs of those lines that persist throughout these iterations. The twin prime conjecture would say that that on at least two of those lines, that there's always pairs. But I don't think you can get from one to the other. I just don't think it's. Maybe someday somebody can do it, but this is not helping. Right? Nothing here is going to help. That's my thought. But I think the rational way to approach like a study of mathematics, if you want to get into this stuff, is to prove what you can prove about what you can prove. get good at proving things, and then go read the literature of what other people have proved, and then use your model of the world to prove the things you know are true from other people's proofs. Maybe you don't know they're true, but then you go through the process of proving it, you'll know why it's true. And at that point, you've given yourself the education that the people who are, what's his name, Kevin Maynard, who's working on the twin prime conjecture and help bring the bound down to around 600, I think. The gap between primes is 600 or less, and then polymath, a bunch of mathematicians got together and led by Terence Tao, and they got the minimal gap down to 264. So there's always there always exists, no matter what number n, no matter how high it is. If you look at all the primes after it, there's always, no wait, am I saying that right? It says the limit of so basically if as the limit of the infimum, so the of the gap between primes. So basically, as you if you're counting from some number n upwards, like if you look at 1, well, the minimal gap between primes greater than 1, the infimum of the gaps between primes. Wow. This is why you use very specific language, right? The infimum, so the limit, the infimum of, let's say, gap between primes, so greater than 1 is 1, because 2 plus 1 is 3, and 2 and 3 are both prime. And if you say greater than 2, well, now it's 2, because 2 plus 3, 3 is greater, and plus 5. 3 plus 2 is 5, right? That's the minimal gap. And then the twin prime conjecture is that n is the minimal gap between n is right. But okay, but you can't just say this. You have to say the limit of this, right? So that because obviously the minimal gap is 1, but once you moved above 1, now there are no more cases where that's true. There's no more gap of 1, right? There's only 2 and 3. That's the only case that ever happens. But then right off the bat, you have 3 and 5, 5 and 7, 11 and 13, so on. And then, but the idea is that no matter how high you make n, those 2's will never go. The gap of 2 will never go away, even though 1 went away. But we don't know that. So all we know for sure is that the gap is something, is some g, right? And g is less than or equal to 264. And that's the best that polymath was able to prove. There's a Chinese guy named Zhang, whatever. He got around 6,000. Polymath moved in, did something. I want to say 6,000. And then Maynard got it down to 600. Polymath 8B came back and improved Maynard's results. They pair programming or mob proving it. They got it down to 264. None of this is formal. But anyway, I don't understand any of their proofs, but they're all based on sieves. Like they're based on the notion of a sieve and um, like algebraic properties of different algorithms that they're able to talk about, but algebraic analytic properties, I guess. And they do a lot of analysis and calculations and stuff, and then they make arguments and they're able to. What I don't see happening, and maybe again, I haven't read all of these papers. I've read a little, read abstracts and things, and I know they work on sieves and but they don't. I would suspect, and maybe I'll be wrong if I read about this more, but very few people are arguing about like the actual. They're not making formal proofs about an algorithm and a particular data structure, right? They're speaking abstractly. They're using analysis. They're not doing the equivalent of formal verification of a computer program, because who does that? The mathematical tools are more they're more abstract, and they're more in some ways more powerful, right? But like here you can, I don't know. I'm not trying to make the case that this is the case, but like I guess what I'm saying is that this is something that is probably not, like, people probably aren't looking at it in this way. And so if you think about it as an algorithm to optimize in different directions, like maybe it doesn't even have to be about optimizing it, but just like having an algorithm that might be wildly inefficient, but it has properties that isolate things that you want to prove. I mean, basically, you're doing a when you write a program, you're doing a constructive mathematical proof, especially when you verify it with it. I don't know. I don't know what I'm saying. It's just like another avenue of attack. I personally am not going to spend. I say that now. It's kind of fun. Like, it's fun to play with this stuff. I don't have any expectations that I don't know. I expect to be able to prove things about this sieve and other sieves, and be able to prove things about sieves in general now. It's kind of fun, so I might keep doing it. I don't have any expectation that I'll make actual progress on anything that's considered mathematically important, if that makes any sense. Right? But, if you go poking your nose around in places that no one has ever gotten to before because they've never, like this is a, nothing, very little here is new. Like I wouldn't even say that I'm not even certain that I haven't created something, that I haven't implemented something here that already exists mathematically, right? I'm sure this idea has been described many times because it's just a basic sieve, right? Like but by being able to identify parts of it, like, and giving them names and identify properties about them, maybe you'll find something, right? And if you go back and kind of, I don't know, Feynman had this advice to people that you just prove things that people already know, or you solve problems that people have already solved, and you just keep doing that, and eventually you get good enough at solving problems that maybe you solve something that nobody's ever solved before. That's way down the line for me. Like, I don't see anything coming out of this that, I mean, obviously, in a sense, if I gave something a name, I give it a specific structure. So, like, probably this exact specific formulation has never been proven before. So I came up with something, but it's not significant, right? It's not like it's Like I didn't discover. I unlikely that I will discover anything new about number theory, right? Or algorithms or anything like that. Like I'm not inventing. I wouldn't even call this a novel data structure. It's any more than any data structure that slap together a bunch of obvious pieces is a novel data structure. A tree, right? A tree and a list and a. It's kind of neat. That's all. It's just it's entertaining. Just I am rambling. Why am I even doing this? You know what? I think I'm gonna just wrap this up because I am rambling. So, yeah, thanks for watching. However much of this you watched, I'm imagining this is like 4 hours now. It says 2 hours and 13 minutes on my clock here, and I don't know how long it was when I was. It's 4:30 in the morning. Thanks for watching.